Okay, one more term here from thermodynamics. We can rearrange our equations that we've been dealing with to get negative T delta S of the universe is the delta H of the system minus T delta S of the system. The Gibbs free energy, we use the letter G for, it's the maximum amount of work energy that can be released to the surroundings by a system. And it's only for constant temperature and pressure. It's often called the chemical potential because you can make an analogy to the storing of energy in a mechanical system. And because we talked about how the delta S of the universe determines if a process is spontaneous, delta G also determines spontaneity. So when our delta S of the universe is positive, our delta G is negative because of this negative sign there. And so a negative delta G means the process is spontaneous. A positive delta G means that the process is non-spontaneous. This equation here is kind of the central equation for this chapter. The delta G is equal to delta H minus T delta S. Like I said, a process will be spontaneous when delta G is negative. There are several ways to combine delta H and delta S to get a negative delta G. If delta H is negative and delta S is positive, then they're working together. It's exothermic and more random, get a negative delta G. If delta H is negative, exothermic, and large, and delta S is also negative but small, then you get a negative delta G and a spontaneous process. Or if delta H is positive but small, so endothermic, and delta S is positive and large, or you're at a high temperature, you can also get a negative delta G. So that's our situation with a endothermic process, so like ammonium nitrate dissolving would fall under that category. And delta G will be positive when delta H is positive, delta S is negative. It's never spontaneous at any temperature. And then when delta G is equal to 0, the reaction is at equilibrium. So you're not getting any change in chemical potential. Here's a table showing what I just talked through, table 17.1 in your book. So we have the always spontaneous, the always not spontaneous, and the ones that, always spontaneous, never spontaneous, I checked the wrong one off, and the ones that are temperature dependent down here at the bottom. Now we can relate our delta G and spontaneity with Q and K. So when we're at equilibrium, then our delta G is 0. We're at a minimum of our free energy. And then for a reverse or a process that is spontaneous, depending on your concentrations, your free energy increases in either direction based on what's happening. Okay, so let's work through some problems. The reaction carbon tetrachloride goes to graphite plus chlorine, has a delta H of positive 95.7 kilojoules and a delta S of positive 142.2 joules per Kelvin at 25 degrees Celsius, which remember is 298K, sorry. Calculate delta G, determine if it's spontaneous. Our central equation, delta G equals delta H minus T delta S. So we're looking for our delta G. Our delta H is 95.7 kilojoules, which we're going to leave as kilojoules. Minus our T is 142.2 joules, which is 0.1422 kilojoules times our temperature, 298 Kelvin, kilojoules per Kelvin. So our delta G, if I do that math, is 53.3 kilojoules, which means we are not spontaneous. It's a positive number. Positive delta G is not spontaneous. In my example here, they did it in joules. It doesn't really matter. Just make sure that your joules or kilojoules in both delta H and delta S. Delta H tends to be reported in kilojoules. Delta S tends to be reported in joules. So make sure that you're converting. Another reaction, the reaction aluminum plus iron 3 oxide goes to solid iron plus aluminum oxide, has a delta H of negative 847.6 kilojoules, delta S of negative 41.3 joules per Kelvin at 25 Celsius, which is 298 Kelvin. Calculate delta G, determine if it's spontaneous. So delta G is equal to delta H minus T delta S. Again, I recommend pausing the video, working this out on your own. Delta G is negative 847.6 kilojoules minus 298 Kelvin times negative 0.0413 kilojoules per Kelvin. So my delta G is equal to negative 835.3 kilojoules. So still spontaneous. Big negative number. If you wanted to make it non-spontaneous, you would need to raise the temperature by quite a bit. I said increase the temperature by quite a bit. Let's figure out how much. So calculate the maximum temperature that this reaction will be spontaneous. So I want to figure out where my delta G goes from a negative number to a positive number. So I'm going to set my delta G equal to 0 because that's where it's going to make the change. And then overall, it will be when it's just slightly less than whatever temperature I calculate. So equals negative 847.6 kilojoules minus T, whatever that is, times my delta S, again, is negative 0.0413 joules per Kelvin. So now I can solve for my temperature. So 847.6 kilojoules is equal to, and my negatives there cancel out, T times 0.0413. So divide by that. And I can get a temperature equal to 2.05 times 10 to the 4th Kelvin. Or 2048. So, yeah, very high temperature. And then you can convert that back to Celsius if you want. Any temperature above 1,775 degrees Celsius will make this reaction non-spontaneous.